In sixth module of chapter 10, we shall learn the continuation of the previous module, that means the application of differential geometry in general theory of relativity and cosmology. Here we shall learn about the Einstein field equation for general theory of relativity, cosmological principle and Will's postulate. Now, here in Einstein's field equation is the relation between the space time with the matter. Here the gravity is a very important part, and just in the previous module we have seen that the space time is pseudo Riemannian space. That means the space is not the positive definite, that means the line element is not positive definite here. So, let us start that how Einstein derived the Einstein's field equation for gravity. So, in module 6 of chapter 10, which is entitled as Applications of Differential Geometry in General Theory of Relativity and Cosmology continued. That means, it is the continuation of module 5, and here the learning objects are the role of differential geometry in derivation of Einstein field equations for gravity. The second one will be the cosmological principle, and the third one will be Will's postulate. Now, there are some main points that Einstein considered to derive Einstein's field equation for gravity, and Einstein observed that it is the deviation from special theory of relativity, and he deviates from special theory of relativity by changing the geometry of the space time. And he showed a description of gravity and its action on matter in a pseudo Riemannian space. So, the underlying space here will be the pseudo Riemannian space. Next one, the field equations in fact describe an equivalence between geometry of space time and matter. So, we can conclude that the geometrization of the gravitational force is the fundamental idea of Einstein's theory of gravity. So, from the three discussions we can see that the geometrization of the gravitational force will be the fundamental idea for Einstein's theory of gravity. And Einstein derived logically the new fundamental physical law considering the pseudo Riemannian space as the geometry of space time, and the logical steps along which Einstein obtained the field equations for gravity are the following. Here the 4-dimensional pseudo Riemannian space is chosen as the space time geometry with a metric such that it is possible to have locally inertial frame at any point. And secondly, the Ricci tensor, which is a 0-2 tensor obtained from Riemann curvature tensor through contraction by the reciprocal tensor of the fundamental metric tensor and which is also symmetric. So, this Ricci tensor R mu nu is a very essential part of the field equation, and this R mu nu contains the second order quasi linear partial derivatives of the metric, which we have seen in our module 5. So, these are the two main conditions considered by Einstein to obtain the field equations for gravity. Now, Einstein at first considered R mu nu equals to k T mu nu as the field equations for gravity, where k is the constant of proportionality and T mu nu is the energy momentum tensor. This one also has been described in our previous modules. Now, in Minkowski coordinates, the conversion equation for the energy momentum tensor is del nu T mu nu equals to 0 . Now, as T mu nu comma nu equals to 0, that means covariant differentiation of T mu nu with respect to nu is 0. This one also we have obtained in our earlier module. Then from the previous equation we have R mu nu comma nu equals to half del R by del x mu. Now, this one is just the partial derivative of the scalar curvature of the space. So, it cannot be chosen as the field equation. Therefore, Einstein tried to find a divergence free symmetric 0 to tensor as a linear combination of the known 0 to tensors, namely R mu nu and G mu nu. That means, the Ricci tensors and the fundamental metric tensors. So, Einstein considered the combination of these two tensors and he took this one capital G tilde mu nu equals to R mu nu plus A capital R G mu nu plus gamma G mu nu as the desired 0 to tensor with A and gamma as constants. Now, G tilde mu nu comma nu, that means the covariant derivative of G tilde mu nu with respect to nu is equal to R mu nu comma nu plus A G mu nu del R del x nu, as G mu nu comma nu equals to 0. So, we have half plus A del R del x mu, and when A equals to minus half, G tilde mu nu comma nu equals to 0, or if you consider G mu nu comma nu equals to 0, then A is equal to minus half. So, we can write G tilde mu nu equals to R mu nu minus half R capital R G mu nu plus gamma G mu nu. And if we replace this one, we get R mu nu minus half capital R G mu nu plus gamma G mu nu equals to k T mu nu. So, in place of R mu nu, we are taking G tilde mu nu equals to k T mu nu. So, this one is considered as the field equations for Einstein gravity. Now, G mu nu equals to R mu nu minus half capital R G mu nu is known as Einstein tensor, and gamma is known as the cosmological constant. Now, there are 10 field equations in 4-dimensional space time due to the symmetry of the tensors involved, but due to the Bianchi's identity, this Bianchi's identity we have learned in our previous modules, there are only 6 independent evolution equations and the remaining 4 equations are the constraint equations. So, only 6 are the independent evolution equations for this Einstein's field equation.
Roll.
An alternative form of the field equations are as follows. Now, contracting the above field equations with G upper mu nu, we have this expression, and from here we can get the value of R, the scalar curvature, which is nothing but 4 gamma minus k T. Now, substituting these values of R, the scalar curvature, in the field equation, we obtain R mu nu equals to gamma G mu nu plus k within the first bracket T mu nu minus half T G mu nu, and this is the another form of the field equations in terms of Ricci tensor. Now, let us consider an example that for the de Sitter space time, we can easily find these Einstein field equations by finding the R mu nu, where the de Sitter space is described by the metric d square equal to dt square minus e to the power 2t by alpha within the bracket dx square plus dy square plus dz square. Now, it is a stationary space time, as there exists a preferential coordinate system t bar, x bar, y bar, z bar defined as t bar equals to t minus alpha by 2 log within the bracket 1 minus 1 by alpha square within the bracket x square plus y square plus z square and e to the power 2t by alpha. Now, a space time is stationary if the space coordinates, that is x, y, z, are independent of time. Now, here if we replace this x bar equals to x e to the power t by alpha, y bar equals to y e to the power t by alpha, and z bar equals to z e to the power t by alpha, then the metric takes the form in this way: ds square equals to within the bracket 1 minus 1 by alpha square and within the first bracket x bar square plus y bar square plus z bar square and third bracket close dt bar square minus dx bar square minus dy bar square minus dz bar square. Now, from this one we can see that the coefficients of dx bar square, dy bar square, dz bar square are time independent. That means, all the metric coefficients are time independent. So, de Sitter space time is stationary. Now, we just in our previous module we have seen that the space time is called static if it is time reversal, it is invariant for time reversal. That means, if we replace t by minus t, the line element is invariant. So, here also we can see that the de Sitter space time is also static. We have just here we are giving the definition of the space time to be static, that if the line element of the stationary space time in the preferential coordinate system has time reversibility, then space time is said to be static. So, the line element in the preferential coordinate system should not contain any product term with dt. So, that is also an important observation. And so, in a static space time we see that all the metric coefficients are time independent and also the line element is invariant under the time reversal. In the previous section we have just learned that the derivation of Einstein field equation in general theory of relativity, and here we have seen the relation of Ricci tensor with the energy momentum tensor and the fundamental metric tensor. Here we have also obtained the concept of cosmological constant. Now, in the next section we shall learn about very important concepts of general theory of relativity, that is the cosmological principle, and another one is the Well's postulate. In cosmological principle we shall consider that the space time will be homogeneous. That means, if we take a hypersurface, that means a one dimensional less, if a space is n dimensional, then hypersurface will be a space of n minus 1 dimension. So, if we consider t as a constant and if we take a hypersurface of our space, here we shall consider that the total space will be a homogeneous one. So, let us see the cosmological principle and Well's postulate. So, let us see the cosmological principle. Now, according to this principle, it states that at each epoch the universe presents the same aspect from every point except for local irregularities. That means, for every point it looks a homogeneous type. That means, mathematically the principle implies that if there exists a cosmic time t and one constructs space like hypersurfaces, that is t equals to constant, then each slice has no privileged points, that means it is homogeneous. Now, here just I have mentioned that hypersurface means a one dimension less space, and when you are considering t as a constant, So, here we can get a space like hypersurface, that means all x, y, z are variable here. So, it is a space like hypersurface, and here we are considering that this space is homogeneous. That means, from wherever we want to see, it looks the same. That means, due to this homogeneity, each slice admits a group of isometries which maps any point into any other point. Which implies that each fundamental observer on the same slice sees identical state of the universe around him. That is, there does not have any preferred direction about any point. So, this is the inner meaning of this homogeneity, or the space is homogeneous, means that for an observer on the same slice sees the identical state of the universe around him. Therefore, according to this principle, each 3 spaces has no preferred point as well as no privileged direction. So, everywhere is homogeneous. A space having no privileged direction about a point is isotropic in nature. In our previous modules of this chapter, we have learned about the isotropic nature and also the spherically symmetric about each point. Therefore, according to this cosmological principle, the space time can be considered into a space like 3 spaces which are spherically symmetric about any point in them. So, this is a very important concept from the cosmological principle. Previously, it is a simplicity principle which states that the universe is both homogeneous and isotropic. Generally, we consider the simplicity principle previously, where the space is or the universe is considered as homogeneous and isotropic. Now, let us see Well's postulate. What it states? That through each space time point there is a unique geodesic of the family, and these geodesics can intersect at singularity either at past, that is when it is Big Bang, or possibly at future, so when it will be a big crunch. So, through each space time point there is a unique geodesic of the family. So, the space time particles possess unique velocity at every point of space time, and hence the space time should be perfect fluid in nature. Now, geometrically, the geodesics of the space time particles are time like in nature and are orthogonal to a family of space like 3 spaces. So, without any loss of generality, the 3 spaces are chosen to be t equals to constant for a typical coordinate system t x1, x2, x3, and the space coordinates x1, x2, x3 are constant along the geodesics, and such coordinate system is termed as co-moving system. And in this coordinate system, the line element of the space time takes the form d square equal to dt square minus h a b dx a dx b, where a b is running from 1 to 3. Where h a b is actually the function of t and x, where t is a cosmic time. So, this is the Wells postulate given by Well. Thus, in module 6 of chapter 10, we have learned about the Einstein's field equation for gravity in general theory of relativity. Also, we have learned the cosmological principle and Wells postulate for general theory of relativity. So, with these things we end this module.